Section 7.5 is the last section in Chapter 7, and this is about creating confidence intervals to estimate a population variance or standard deviation. So in this section, we're going to introduce a new distribution. It's called the chi-squared distribution, and this one looks a little different than the t-distribution and normal curve that we've been working with. The test statistic for a chi-squared distribution is given by this equation here. Chi-squared is this fancy man's x here with a squared on it, and it's determined by n minus 1 times the standard deviation of the sample squared divided by the standard deviation of the population squared. The main difference with the chi-squared distribution is it's not symmetric. It's a distribution that's skewed to the right. Just like t-distribution, there are an infinite number of them. It varies with the sample size and degrees of freedom. And as the degrees of freedoms increase, the distribution becomes more symmetric. Values of chi-square cannot be negative. It starts at 0 and it gets larger as we move to the right. Degrees of freedom is given by n minus 1. First things first, let's figure out how to read this chi-squared table. We want to find the critical value of chi-squared separating 2.5% in the left tail, so 2.5% over here, and 2.5% in the right tail. 2.5%. The sample size is 21. Here's our table. Now, one thing that's different about the chi-squared distribution is that it's always telling us the area to the right of our cutoff. So if we want the value, a critical value for this cutoff right here, if this was a normal curve, it would be telling us how much is to the left. It was always to the left. In the chi-squared distribution, it's always the opposite. It's how much is to the right of this. So if we want to find the cutoff for this 2.5% to the left of that curve, with a sample size of 21 and 20 degrees of freedom is just one less than the sample size. So 2.5% in that left tail, that means that there is 97.5% to the right of that. Okay, so I'm just doing 1 minus 2.5% to get everything that's this way. Okay, now if you look at the top here, it says this alpha, and we can see this one here is 97.5%. Degrees of freedom is 20, so our chi-square value for that left side is 9.591. We want to do the same thing for the right tail. Now the right tail is easy because there's just 2.5% to the right of that value. So if we just keep going over on the same line till we hit 2.5%, the chi-square right value is 34.170. Okay, there's two values in these cutoffs. Let's do another one. The critical value of chi-squared separating an area of 5% in the left tail and 5% in the right tail if the sample size is 25. 5%. All right, here's our table. Sample size is 25. That means 24 degrees of freedom. We're way at the bottom of this table here. Okay, and there's 5% to the left. So that means, oops, I clicked the wrong button there, but there's 95% to the right of this. Here's 95% up top. We're going all the way down to the bottom where it intersects with 24 there, 13.848. Okay, this only has 5% to the right there. 5% is right here. Make sure you're not looking at that because that's 0.5%, 36.415. Now in this chapter, it's talking about a p-value, which we really haven't touched upon yet, but let's go ahead and give it a try. So we have a chi-squared test statistic of 30.937. So that's telling us that chi-squared equals 30.937. Sample size is 16. What's the p-value for that, and how does it compare to 5%? So if we look at this table, sample size is 16 means we have 15 degrees of freedom. So we're on this line here. Now if we look at this whole line, it's telling us up here the chi-square value is 30.937. So where would that go on this line? All right, well 30.937 is right in between these two. Okay, it's above 30.5, but it's less than 32.8. And that tells us our p-value is in between those two numbers, in between 0.005 and 0.01. One more of those. Estimate the p-value for a left-tailed test with a chi-square test statistic of 9.799 if the sample size is 19. How does it compare to a probability of 10%? All right, so this time we have, when it says left-tailed test, it just means that we only care about this side. Sample size is 19, degrees of freedom are 18, so we're on this line. And where does 9.799 fall on this line? Okay, well, it's greater than 9.39, and it's less than 10.865. So it's somewhere in between here. Okay, and that means that there's somewhere between 10% and 5% to the left of this line. All right, so our p-value would be something in between 5 and 10%. When it asks how does that compare to 10%, we know it's lower than 10% because the highest it can be is up to but not equal to 10%. All right, let's make a confidence interval. We can make one for the variance, which is this top equation, or the standard deviation, which is just the square root of this top equation. Here we have a sample of 55 Skittles. We find that they weigh an average of 1.062 grams with a standard deviation of 0.0528 grams. Use the sample data to construct a 90% confidence interval for the population variance of all Skittles. Okay, so now we've been doing confidence intervals for population means and population proportions. When this word is either variance or standard deviation, that's when we use this method. It's also giving us some extra information. It tells us what the average weight of these Skittles are, and we don't need to know that. That's kind of useless information. So sample size is 55. Standard deviation from our sample is 0.0528 grams. And degrees of freedom is 54. Closest thing in our table is 50. We want a 90% confidence interval. 90% is cut out of the middle. And that means that there's 10% left over, 5% on this side, and another 5% on this side. All right, so we would go to our table. We would go to 50 degrees of freedom, since that's the closest thing to 54. And we would look up to the right of that cutoff. Okay, and there's 0.95 to the right of that. Okay, do the same thing for this 5%, and we get our two chi-square values. Now we're going to plug everything into this equation. 55 minus 1 times 0.0528 squared. Just a note, right chi-square value actually goes on the left of this equation because we want the smaller thing to be on the left, and this is always going to be bigger than that. So if we divide by a larger number, this fraction will be the smaller one. We want smaller on the left, larger on the right. Also note, we're not actually squaring this. It's called the chi-square value, but we don't square the value. Simplify both those fractions. We find out that sigma squared, which is the variance, is between 0.00223 and 0.00433. We are 90% confident that the true variance in weights of Skittles lies between 0.00223 grams squared and 0.00433 grams squared. Variance is always dealing with units squared, and that's not very helpful to us because what is a square gram? So instead, let's find a 90% confidence interval for the population standard deviation. So we're just going to take our interval that we had just gotten, and we can find the standard deviation by just square rooting the variance. So standard deviation is just sigma. If we square root sigma squared, those two cancel. And we get 0.0472 to 0.0658. We are 90% confident that the true standard deviation in weights of Skittles lies between 0.0472 grams to 0.0658 grams. If we're asked what sample size we need to get a result within a certain margin of error, these problems are really nice and easy. It just gives us this table here and we look it up in the table. For example, we want to estimate the standard deviation sigma of all voltage levels in a home. We want to be 95% confident that our estimate is within 20% of the true value of sigma. These are the key things. How large should the sample be? So we look at this table. We're estimating sigma. Now, if you look at this table, one side of the table is about sigma squared. This is not the side we want. We want the side that's about sigma. Okay, now there's two options. We have 95% confidence and 99% confidence. This problem we want 95%. Okay, so we're in this box, top right. We want it to be within 20%, so now we're just looking at 20%, and we're saying our sample size is 48. One last one, we want to estimate the variance of all senior GPAs at High School South. We want to be 99% confident that our estimate is within 10% of the true value of the population variance. How large should the sample be? Variance is the left side of this table. Standard deviation is this side. We can cross that one out. We want to be 99% confident. This one up here is 95%. We want 99%. And we want it within 10%. So our sample size is 1402.